Hey, want to know a secret right now? Two particles, light years apart, are still connected. One is spinning clockwise, the other counterclockwise. If you measure one and find it spinning clockwise, you instantly know the other is spinning counterclockwise, no matter how far away it is. Einstein called it spooky. We call it quantum entanglement. Quantum mechanics is weird. From the smallest atom to the largest star, everything in the universe is made of particles that follow the rules of quantum mechanics. And those rules say that particles can be in two places at once, or spin in two directions at once. But what happens when those particles get separated and then you measure one? Which direction was it spinning? This has kept scientists scratching their heads for over 100 years. But before we get into the quantum physics, let's take a step back and look at classical physics, the physics of everyday life. Let's say you have a coin. Before you flip it, it's both heads and tails. But once you flip the coin and it lands, it's either heads or tails. In this case, the coin is our particle, and whether it lands on heads or tails is its property. It's a characteristic of the coin. In quantum physics, though, things are a bit different. Let's imagine a particle that can spin around an axis like a coin. Now, before you measure which way it's spinning, it's both ways. But the moment you measure it, it stops spinning. Why? Because you've forced it to choose one state or the other. This is called wave function collapse. But there's a twist. Imagine you had two particles, each spinning around an axis. Now, if you measured the first particle, you would force it to stop spinning. But because they're linked together, the second particle would also have to stop spinning. Same goes the other way around. If you measured the second particle, the first would also be forced to stop spinning. So here's the question. What if you didn't measure either particle? Would they both keep spinning indefinitely? Or do they only start spinning when you look at them? The answer might surprise you. They spin, even without being measured. But it's not quite like you would expect. In quantum physics, a particle's properties are described by a wave function. This wave function contains all the information about the particle, such as its position and momentum. And according to the math, this wave function doesn't collapse until you actually measure it. Till then, it evolves according to the Schrödinger equation, which governs the behavior of quantum objects. Now, remember those two spinning particles? Their combined wave function could describe them spinning in any combination of clockwise and counterclockwise. For example, it could describe both spinning clockwise, both spinning counterclockwise, or one spinning each way. This means that before you measure them, these particles are in a superposition of states. It's kind of like a blurry mix of all possible spins. When you measure one particle, you force that particle to choose one state, say clockwise. But what happens to the other particle's wave function? Does it collapse too? Well, according to some interpretations of quantum mechanics, yes, it does. The other particle is forced to choose the opposite state, counterclockwise. That's spooky indeed. This is because the two particles are entangled. Entanglement is a special connection between quantum objects where the properties of one object depend on the properties of another object, no matter how far apart they are. Once you measure one entangled particle, you know instantaneously what state the other particle is in. To be clear, you don't actually see the other particle change, you just know its state has changed. This is because you can't actually see the state of a quantum object. All you can do is measure it. And the act of measurement forces the object to choose one state or the other. Entanglement is what makes quantum computing so powerful. By exploiting entanglement, quantum computers can perform calculations much faster than classical computers. This is because entangled particles can be in multiple states at once, which allows them to explore many possible solutions to a problem at the same time. Entanglement is also what makes quantum cryptography so secure. By sharing entangled particles with another party, you can guarantee that any attempt to eavesdrop on your communication will be detected. This is because if someone tries to eavesdrop, they will inevitably disturb the entangled particles, which will change their state. But not everyone agrees that entanglement really works this way. Some physicists argue that entanglement isn't real, but rather an illusion caused by our lack of understanding of quantum mechanics. They believe that the wave function only collapses when you actually make a measurement, not just when you have the opportunity to make a measurement. For example, consider the double slit experiment. When you send single particles through the double slit, they create an interference pattern on the screen behind the slit. This interference pattern shows that particles are in two places at once, like waves. But when you try to measure which slit the particle goes through, the interference pattern disappears. This is because the act of measurement forces the particle to choose one path. Some physicists argue that this choice is made by the particle itself, while others argue that it's made by the measuring device. But regardless of who makes the choice, the result is the same. The interference pattern disappears. However, there is evidence that supports the idea that entanglement really is real. For example, in 2015, physicists at the University of Vienna carried out an experiment that showed that entangled particles remain linked even after being separated by 1,400 kilometers. They did this by sending entangled photons through two different fibers, one through a 97 kilometers fiber and the other through a 1,300 kilometers fiber. At the end of each fiber, they placed a beam splitter that split the photon into two parts. Then they sent one part of each photon to two different detectors. They found that the photons were still entangled, even after being separated by 1,400 kilometers. There are many more experiments that support the idea that entanglement is real, but you get the idea. Entanglement is a strange and mysterious phenomenon that continues to baffle scientists. But it's real nonetheless. And that's why when you measure one entangled particle, the other particle instantly chooses the opposite state, no matter how far away it is. Einstein called it spooky action at a distance. We call it quantum entanglement. But now it's time for you to make a choice. Do you think entanglement is real or just an illusion? Let us know in the comments below. And if you want to learn more about quantum physics, check out our other videos. For example, did you know that quantum physics predicts that time can flow backwards? It's true. There is a process called quantum tunneling that allows particles to move through barriers that would normally be impenetrable. This means that particles can go from being less likely to more likely, which is the opposite of how things normally work. Or maybe you want to know how quantum physics could help us create new drugs. It's possible. Quantum computers could help us simulate the behavior of molecules at the atomic level, which would allow us to design drugs that target specific molecules in the body. Whatever you choose to do, we hope you continue to learn and grow. Thanks for watching. We'll see you next time.